we're really looking at an application now that's directed like your physics anyway. So we'll just look at this opening problem and think about it from the physics slash maths way, and then try and link some stuff together. But if you do think about it as like projectile motion type stuff, it'll help you to perhaps visualize and think about what we're doing. We're going to do some calculus, we're going to do it on the vectors, but really it's no new calculus skills, it's just splitting it up into its two components. It's really all we're doing. So like an example like this where a cannon is fired from the top of a cliff, you could have an initial velocity and you might break it up into its horizontal and vertical components, or the way that we're going to do it from the maths point of view is think about it as being parametric equations, where you've got the equation for x and how that varies with time, and the equation for y and how that varies with time, which is the same idea in physics, but this is just a bit more of a mathematical way of thinking about it. So we've got this example here where you've got the cannonball being fired off a cliff, okay, and you've been given the two parametric equations. And both of those are your x and y are in meters, t is in seconds, very physics-like. The first thing it asks is what are the coordinates of the cannonball when it's first fired. So for those, well, t is obviously going to be 0. So it's just a case of, for A, just saying, well, the position was at t equals 0, x is equal to 3, and y is equal to 28. Okay, so that's its initial position, nothing more than that. What speed did the cannonball leave the cannon? Okay, that's when we need to say, okay, well, normally in a physics question you're given that. Okay, what we've been given is how the position is changing as time goes along. But really, then, if we want to know if it's how position is changing, well, that's that is the rate at which that changes is your speed. So if we just find the derivatives of both the x part and the y part, but individually, then we're going to get how that speed is changing, and we're going to get it how it's changing in the x direction and how it's changing in the y direction. So for part B, really what we want is the derivative of x, which is going to be equal to just 183, and the derivative of the y, which is equal to minus 80, not minus, I don't know why we're at minus 87, take 9.8 t. And that's pretty nice because that relates directly to our sort of physics. So obviously this is done on Earth because what we've got, if you think about it, is in the x direction, effectively you've got something travelling 183 metres a second horizontally, and you've got something that is accelerating at 9.8 metres per second down, which is the negative. But we also know that it started with a initial vertical velocity, okay, of 87. So it's it relates directly to your physics, but we're just breaking up the maths a little bit different. How long did the cannonball take to hit the sea? Okay. What we want to do then is say, well, we want the time for when the y, because that's the y component, we want that to be at 0. Okay, so I'm not going to solve this one because what we're going to end up with is that 28 plus 87 take 4.9 t squared must be equal to 0. So you get a quadratic, and you'd solve a quadratic formula or whatever to solve. Okay, what was the range? Well, a bit like in physics where you had to, oh, hang on, now I've got this time. And if you remember from the physics point of view, you always wanted that time to link between horizontal and vertical components because time is not a vector. And so you could just say, well, if I know that at time, whatever that ends up being, 5 seconds or whatever, who knows, when it hits the water, well, I want to know how far it's gone. Well, I bring that 5 across and put it into the x and say, well, 3 plus 183, lots of 5. So I'm using that information. So it's it's another way of describing it. It's quite powerful. You can see it. That one of the last bits says, what's the advantage of describing both x and y in terms of t rather than writing y in terms of x? Well, if you write y in terms of x for this, you lose the time factor, and so you can't see the changes and plug them in. Okay, so we're going to be doing some stuff like that. This is just a reminder. And this is the first part, and I don't really want to do any questions from here. Just as a reminder about parametric equations, because we've used them, and that was our last topic, or 2 topics ago, I suppose. But if we had a parametric equations, these are all going to be in 2 dimensions, so that makes it pretty straightforward so far. As an example, if we had a line that was going to go through the point 2, 4 and had a direction vector of 3, 1, then we can write that as 2, sort of a point, plus 3 lots of t for the x, and for the y it's 4 plus t. Okay, t's got to be a member of real, and in fact, probably on top of that, in this case, mostly t is going to be greater than or equal to 0. All right, because we're mostly going to be doing stuff with time. And we can write that into vector form. So what does that mean? Well, for parametric equations, we can actually use parametric equations to define a curved line, not just straight lines. So if we've got this set of parametric equations here, just going to do it really quickly, then if I just put these points, it tells us that it just wants us to plot the motion from t equals 0, 1, 2, and 3, and that's as far as it wants to go. So orbit of a satellite. Then to plug those in at 0, t is equal to 0, so x is equal to -2. If I just keep going down the x spot there, then at 1 it's going to be equal to -1, 0, 1, and then the y's, 0 is going to be 12 on 1, which is 12. I'm going to have 12 on 2, which is 6, then 12 on 3, 4, and then 3. If I plot those, just so we can sort of see the curve, at -2, 12, -1, 6, 0, 4, and 1, 3, you can see there's that sort of curve that's been plotted. Okay, not very nicely drawn, but that's the idea. So you can plot a curve using parametric equations, and certainly we just showed before that we could use the parametric equations to plot that nice parabola that you would get from projectile motion. So that's just to introduce them. That is the first subchapter of the last chapter. I don't really do any questions from it. And that's just to remind you for that. The next 2 subchapters talk about having pairs of quantities that are varying. The first one is when they're uniformly varying. So what that's talking about is if you have, as x changes, y changes by the same amount. Effectively, if you plot it, you're going to get a straight line. So you can plot a straight line with parametric equations as well. It would sort of seem a little bit pointless because it's like making the maths more complicated than it needs to be, but it works and we can show it. And once again, I don't really want to. We'll have a quick look at this example here, and then I'd say I wouldn't do anything from that. We'll go to the next one. But the important parts that we need to be, thinking about and aware of are just that the initial position is going to be, x at time 0 and y at time 0. So just plugging them in, and the velocity vector, okay, is going if you're given with a velocity vector of a, b, okay, then we can write that set of parametric equations like this. So our initial x position plus the x part of the velocity vector times by time, and same thing for the y's. Okay, this part is probably the the more important part, and that's to say that the speed of the object is the absolute magnitude of the velocity vector, which makes sense. But in these ones, when you've got a straight line like that, it's going to be the same velocity the whole time. So it's constant velocity type questions. Okay, and it's just going to be just like you would do in physics. You'd break it up into its horizontal component and its vertical component, and you'd use Pythagoras and you'd say that's the size. Okay, the square root of a squared plus b squared, a squared plus b squared equals c squared. It's the same maths. Okay, but we're just thinking of it from a vector point of view. So in the first question, the first example, and I'm not even going to do a question from it, I'm just going to look at the example because then we'll do a question that's similar but the more challenging style. Then we can go through and we can see some of the relationships. So we've got a particle that moves with those the parametric equations. So x position is 2 take 3t, y is 2t plus 4. Okay, because they are just linear equations themselves, when we come to get their velocities, so the derivative of x, the x part, and the derivative of the y part, we just get constants. This tells us that the velocity is constant. Okay, so the initial position, if we look at, okay, a little bit smaller so we can just see it all. The initial position is just when x equals 0 and y equals 0. All right, so we're just going to plug 0 into here and 0 into here, pretty straightforward. Okay, so the initial position is at 2, 4. The velocity vector, we read that directly off of here, so -3 and 2. Okay, just note that they've written these two in, the t and t's in a different spot just to make it neat and tidy, so that the x one doesn't say -3t plus 2, but it would be the same thing. So that's pretty straightforward. You could, this says illustrate the motion. I don't think you're ever going to get a question that asks you to illustrate the motion, but if we look at the motion that's illustrated here, as x varies, y varies by the same amount, so we get a straight line. Okay. You can see that. Speed, okay, when we want to work out the speed, what we're doing is we're looking at the velocity vector here, okay, and using that here. Okay, so -3 squared plus 2 squared, all under the square root to get it back. It's effectively Pythagoras. Okay. Then E says find the Cartesian equation of the path of P. All right, so effectively turn it back into a straight line equation. Well, that's okay if it's a straight line. I don't know. I don't think you get any questions about straight lines, so I wouldn't get too strung up about it. But you can have a look at that process and see, okay, I can write it back into the normal old, slope-intercept form type of equation. So the one that I want to actually sort of go through a bit more is part C, and they're the ones I want you to do some questions from, is when they're non-uniformly varied. Okay, and so where something is changing differently compared to, so the y component is changing differently to x. Projectile motion is your classic example of that, where things are accelerating due to gravity, but they're not changing in the horizontal direction. So this is just this little bit is just an example of a projectile motion one. The one we'll go through is just a random one. It's not going to follow projectile motion. In fact, the path it would take would be different again, and that's okay. So we've got just a couple of equations there. Okay, filled out the table like we did before, and we can see the path that it takes. That nice parabola that it's got there. Okay, the things that are important from it, okay, is that just like, there's classic physics questions that say draw a velocity diagram, velocity vector on this path, and you know that what you do is use the tangent at that point for the direction. Okay, and it's a bit hard to see up on that screen, but the green velocity vectors, they're going to change their length, okay, because we know that the velocity in the vertical direction is varying. Horizontally, they should all go across the same way in the x, okay, but their length in the in the y is changing for each position. So you've seen that before, but that sort of follows through with what we've got. The velocity vector, okay, we can find by doing the derivatives of the x, because remember that x with respect to t is the displacement, the position in the x at different times. So the derivative of that is going to give the velocity in the x. Okay. So there's an example, just using that example there, then the derivative of the x is just going to become 2. The y is going to become negative 2t plus 4. Okay, so the velocity vector here is 2 minus 2t plus 4. So we can have, and you're going to see velocity vectors that have that parameter t still in them, because it's going to vary at different times. The velocity at different times is going to be different, particularly in the y for projectile motion type ones, but it could be just another example where the x one is changing as well. Okay, we already said this, that the speed is going to be equal to the absolute length of the velocity vector. Okay, it does have in that bit there where it's got the square root of v dot v. Okay, the velocity vector dot velocity vector. Really, that's sort of, you probably don't really need to remember it, but that comes from the velocity section where we said if you do a vector dotted by itself, then effectively you get the square of the length of that vector. Okay, so if you get the square root, you get a length of the vector. But effectively, what are you doing? Well, you're actually going to go and say, right, I need the x component, all right, of the vector, and then the y component of the vector. Square them, add those two values, and get the square root. Effectively Pythagoras still, and we'll get the actual speed that it's going at. Remember, that's speed because it doesn't have, that's a value of its length, it's not its direction. Okay, so I've already filled that in anyway, but you can get the 2 from up there that I just did 2 squared, all right, and this is the speed at t equals 4, okay, but the 2 is 2 because the x is always 2, it's a constant. The other one is negative 4 because we've got negative 2 times 4 is negative 8 plus 4 gives you your negative 4. So negative 4 squared, and you get the square root of 20. So that's the speed. Okay, well, and for direction, it's just tangential to the curve. Unless you've been given some other information that you can work out a direction, then that's what you're going to get. It's only asking for speed anyway. So what I want to do is go through this example, and then give you some time just to have a go at these. And I think you'll probably find these not too challenging, really, considering you all do physics. So we've got 2 equations. This time, though, if you look at them, you can see that the x and the y are both quadratics. Okay, and the course pretty much says that it's not going to go any higher than up to a third degree polynomial. So you're not going to have challenging parts in here to do for it. It tells us that time is only between 0 and 3 for whatever reason, and the distances are in centimetres for whatever reason. Okay, and it's just a particle, so there's no real life correlation to this, I suppose. So initial position. Okay, just when it's t equals 0, so therefore you've got the position is just going to be 2, 21. Simple. Part B, the initial velocity vector and speed of the particle. Okay, so if I want the velocity vector, I'm going to need to work out what is the derivative of those two. Really, that's the velocity vector. We just need to work it out. So that's equals v, which is equal to, what are we going to have? So 3 plus 2t and 3 take 4t. Okay, so that's your velocity vector. that's the initial velocity, well, that's the velocity vector, to be honest. If you only want the initial, therefore initial velocity vector is equal to 3, 3. Okay, because that's when time equals 0. We know that velocity vector changes as time goes along, but it starts at being 3, 3. And it wants to know what is the speed initially as well. Okay, so therefore initial speed is equal to the square root of 3 squared plus 3 squared, which is equal to the square root of 18. Okay, and t doesn't even say that t's in seconds, does it? No, so, it does say 1 second. The question doesn't actually say, but we assume that's in seconds for this. So I guess we should say that the initial speed is this many centimetres per second. Okay. So that was pretty straightforward. Part C, find the final position and speed of the particle. Okay. Because we know that t only goes between 0 and 3, then at 3 seconds must be the final time. Okay, so if we want the final position, we just want it at t equals 3. Okay, so the position, the x position at 3 is going to be 2. I've got this written down so I don't have to see it on the screen. But obviously we would need to use those equations and plug it in. Okay, so that's going to be equal to, that equals 20, and the y at 3 is equal to 21 plus 3 lots of 3, 2 lots of 3 squared. That equals 12. Okay, so the final position is at 2012. So we've got an initial position and we've got a final position. Okay, the final speed is going to be equal to the square root. Okay, and what we need to do is go back to our velocity vector here. Okay, and say, well, at time equals 3, we're going to have 3 plus 2 lots of 3. It's the x part. Okay, so we'll just square that, plus 3 take 4 lots of 3 squared. Okay, so that's going to be equal to the square root of 9 squared plus negative 9 squared, which is square root of 162, which would simplify down, but I can't bother simplifying it down, but you can simplify it down to whatever that comes out to be. That's our final speed, so that's C sort of complete. D says comment on the particle's acceleration vector during the motion. So we've just been working with doing the first derivative, but no different is to say, well, the acceleration vector is just going to be equal to the second derivative of the y and t. Okay, so that's going to be equal to, we don't have to just comment on it. We can look at it and say, well, I know that that's just going to be 2 negative 4. Okay, but I would suggest that if they're asking you to comment on it, you'd say, well, it's got a constant acceleration. Okay, of 2 centimetres per second in the x direction and negative 4 centimetres per second in the y direction. Okay, but you can, like, all we're doing is just breaking it up into its 2 components and then dealing with it. So we've done acceleration. Find the particle's speed after 1 second. Okay, so e at time equals 1 second. We want the speed, so speed is equal to the square root, and we'll just go back up here and remember our velocity vector. Okay, and if I put in 1 at these 2 points, I'm going to get 3 plus 2 is 5, and 3 take 4 is minus 1, so 5 and minus 1. So 5 squared plus negative 1 squared. 25, 26. Okay, so that's my speed after 1 second. Okay, so I've done all that work. That's pretty much just plugging stuff in. The last part is really just going, okay, well, now you've done that, let's think back to stuff that you were doing even in methods. What about finding the max and minimum speeds? We've got to find the max and the minimum speeds of this particle during its motion. Okay, so for this, if we want the maximum and minimum speed, okay, then we're going to have to think about, okay, what are the how does the speed work? How do we calculate the speed? Okay, we calculate the speed by doing the square root of the velocity vector squared, add the 2 components. Okay, so if we want to see how the speed varies with time, okay, we need to have F. We really want, and what's its lowest speed, isn't it? Find the maximum speed. We want to know, we really want to know that, don't we? We want to know how the speed is changing with respect to time, but we want that to be equal to 0 to find the maximums and minimums. Okay, so we've got to be able to write what we've got now. We've got to be able to write the velocity and then work out what its derivative is, okay, with respect to time. So our velocity is going to be equal to, remember, it's the square root of this component, which is, reminding myself, 3 plus 2t squared plus, it's 3 take 4t, wasn't it? Yeah. Okay, that's what velocity equals. So therefore, what does our our derivative of that velocity equal? Okay, now I wouldn't want to do it directly from that part. Okay, I would write that velocity is equal to 3 plus 2t squared plus 3 take 4t squared all to the half. Okay, and well, you could leave it like that, or you could expand out the brackets. We could leave it like that because we just have to use a chamber lots of times to be able to do it. I don't know, maybe we'll expand it out just to make it easier to see. So V is equal to, we have 9 plus 4t plus 4t squared plus 9 take 8t plus 16t squared to the half. 9 plus 9, so we've got 18 plus 4t, take 8t is negative 4t plus 4t squared plus 20t squared all to the half. So now it's a bit easier to deal with. So derivative of that velocity is going to be equal to half lots of 18 take 4t plus 20t squared all to the negative a half times by negative 4 plus 40t. So that becomes negative 4 plus 40t all over 2 lots of 4t plus 20t squared to the half. But we want dv dt to equal 0. So therefore, because we want it to equal 0, we've got all that mess at the bottom, but who cares? Okay, because we're saying it's minus 4 plus 40t equals 0. So therefore, 40t equals 4. T equals 4 on 40. T equals 1 on 10. Now, I'm not sure. I feel like I did that earlier and it wasn't quite that answer, but that's right. Something along those lines. That's the process anyway. But we go back to a question, and our question says, what's the maximum and minimum speeds of the particle? There's two values. Yet, we've only got a time for one. Okay? What that tells us is that within that time frame, between 0 and t equals 3, you're only going to get a maximum or a minimum. We can think about which one that's going to be in a second, but you're only going to get a maximum value or a minimum value. The other one is going to have to be one of the two extreme ends. Okay, if whatever the speed was at time equals 0, or whatever the speed was at time equals 3. Okay, just go back, make sure I have 20. I think. Now I can't remember whether it was t equals 1 on 10 or not was the right answer. But what we need to do is say, okay, well, is that a maximum or a minimum? Well, we should really go back into our equation here, which is a bit messy to think about, but we should plug something in there to try and work it out. So if I was going to put in, if I put time as equal to 0, then that makes that pretty easy to get a value for. So time is equal to 0, then what do I got? If I look at that top line, I've got 18, so I've got square root of 18, that first bracket, but it's on the bottom, the square root of 18, so 2 lots of the square root of 18, and the top line is going to be negative 4, so it's going to be negative over a positive. Okay, so if I do a sign diagram here, this is at 0, this would be at 3, it's not to scale, then we're saying that's negative. Okay, if I put t is equal to, say, 1, the bottom line, no matter what, has to be a positive value, doesn't it? Okay, so if t is equal to 1, I've got negative 4 plus 40, which becomes positive. So what that tells us is that we have a negative slope, positive slope, so therefore this is the minimum. Okay, that's where the minimum occurs. So the maximum is either going to be at time equals 0 or time equals 3. Okay, and we already have velocities for them, I believe. Didn't we work them out? We have the final speed at time equals 3 is the root of 162, and the initial speed was the square root of 18. So the square root of 162 is going to be bigger than the square root of 18, so it's got a higher velocity at time equals 3. Okay, and it says finds them. You would now put 1/10 in there, but I'm going to stop. at that point, you can put that in. Okay, that's probably as challenging as that chapter gets, and it's as challenging as A, B, and C from chapter 9 gets. And really, I just want you to do a little bit of that, make sure you're okay with it, so we can move on.